Well, thank you very much for that welcome, and thank you for your invitation to come up to Scotland and to speak here in this great city, and a city that obviously has many geological connotations, many geological associations over the years. So it's great to come here and be able to talk to you on this subject of geology. Now, somebody is telling me they can't hear very well. Can you hear me okay? Yeah? Is the microphone working? I'll speak up slightly. Okay. Well, the subject this evening is the Grand Canyon, evidence for the global flood. So we're not really dealing with the geology of Scotland, some local geology. We're going a bit further afield. And we're going to Arizona. The Grand Canyon in Arizona is one of the world's greatest natural wonders, of course. And about 5 million people every year visit the canyon and wonder at the magnificence of the spectacle that's spread out before them. The sheer size and the majesty of the canyon have a tendency to overwhelm the visitor and surpass your ability really to take in the sight that's spread out before you. Now, one of the questions that commands our attention at Grand Canyon is what on earth it all means. How did the rock layers that make up the canyon come to be there? What story about the past do these rock layers reveal? What is their origin? Now, the explanation that's presented to most visitors involves slow processes operating over very long time periods, periods of hundreds of millions of years. However, in this talk, I want to propose that there is an alternative explanation for the Grand Canyon and for its rock layers, an explanation that involves catastrophic geological processes operating over relatively short timescales. And I want to suggest that gives us an alternative explanatory framework that helps us to understand the geology that we have laid out before us. Now, here in this first slide, we see these two competing interpretations of the geological record in diagrammatic form. In the middle of the screen, you see the standard geological column, a somewhat simplified version of it, with the Precambrian rocks, the Paleozoic rocks or primary rocks, the Mesozoic or secondary rocks, and then the Cenozoic rocks. And on the right, you can see the evolutionary or long age interpretation of this geological succession. Now, the evolutionary or long age view sees the rocks and fossils as a record of evolution over geological timescales. And this perspective is founded on the principle of uniformitarianism, the idea that the present is the key to understanding the past. In other words, we observe today the laying down of sediments in modern-day rivers, lakes, oceans and deserts, and we assume that the ancient fossil-bearing sediments, like those that we see exposed at Grand Canyon, were formed by similar processes and at similar rates and intensities to those that operated in the past. What is normal or average today is assumed also to have been normal or average in the past. Now, of course, if that uniformitarian principle is correct, then the rock layers of Grand Canyon must have taken tens or even hundreds of millions of years to have been laid down, because sediments today are accumulating in these modern environments on average very slowly. So for many people then, Grand Canyon, with a mile-thick succession of sedimentary layers, is a showcase for slow and gradual geological processes acting over long time spans. However, on the left of this diagram, we see the alternative view, or one alternative view, the creation or the young age interpretation of the geological record. While the uniformitarian geologist adopts the idea that the present is the key to the past, the biblical creationist sees the rocks and fossils instead as snapshots of depositional events at specific times in biblical history. Notably, he interprets a large portion of the geological record as the product of a global flood, the flood that's described in the Bible in Genesis chapters 6 to 9, with other parts of the record representing pre-flood and post-flood deposits. And although there's today still a great deal of debate among creationists about precisely where these boundaries between the pre-flood and flood and post-flood sediments lies in the geological record, the view that I've represented here is one major strand of thinking within creationism, with most of the Precambrian rocks representing Creation Week and pre-flood deposits, and the uppermost part of the Precambrian through to the end of the Mesozoic representing flood rocks, and then with the Cenozoic rocks representing those that were formed in the post-flood period. Now, in this catastrophist framework, the present is not viewed as representative of the Earth's past. Instead, there's perceived to be a major discontinuity between the past and the present. The global flood described in the Bible is accepted as a real and unique event that was responsible for depositing many of the Earth's sedimentary rocks, including many of those that we see in Grand Canyon. So in my talk today, I want to describe just some of the geological evidence, and I have had to be selective for reasons of time, that appears to be consistent with this catastrophist interpretation of the geological record. Evidence which offers us, I think, some helpful insights as we seek to understand the geology of Grand Canyon. But before we look at the evidence in detail, I thought it would be helpful to begin, first of all, with an overview of Grand Canyon itself and its environs. So here we have a map of the Grand Canyon in its setting in the state of Arizona. Grand Canyon stretches 277 miles through northern Arizona, from Lake Powell in the east right through to Lake Mead in the west. The main portion of Grand Canyon attains a depth of more than a mile, and it ranges from 4 to 18 miles wide. And Grand Canyon, along with its 60-mile connection here through Marble Canyon, isolates virtually the entire northwestern corner of the state of Arizona. This is a photograph that I took at sunset on the south rim of Grand Canyon at a place called Mather Point. The south rim of Grand Canyon is at 7,000 feet above sea level. The north rim is just a little higher at 8,000 feet in elevation. And the Colorado River cascades along within the canyon at about 2,500 feet above sea level. And within the canyon, as you can see here, there's a host of pinnacles and buttes, canyons within canyons, precipitous gorges, and ravines. The most spectacular of these pinnacles or spires are sometimes referred to as temples, and some of them tower up to a mile or so above the level of the river. Now, of course, this is a desert landscape, and what that means is that we don't have very much vegetation. And of course that's great for geologists because it means that the rock layers are exposed magnificently to view, and also for the photographer it allows the sunlight to pick out the varied colours and hues on the rock. And as you watch the sun go down over the canyon, the colours just seem to change all the time. It really is a magnificent sight. Well, let's think then about the geology of Grand Canyon. Grand Canyon exposes a thick sequence of Paleozoic sediments, beginning with the Tapete sandstone here and going up to the Kaibab limestone, which forms the rim. These horizontal sedimentary layers sit on top of an eroded basement of older Precambrian rocks, including sediments, Precambrian sediments like the Bass limestone, the Hacketai shale, the Shinamou quartzite, the Docks formation. There are also igneous rocks like the Cardenas basalts, which are lavas, and various sills and dikes that have been intruded into these sediments. There are also igneous rocks like granites, the Zoroaster granite, and also the oldest rocks are thought to be these various schists like the Vishnu schist. They're metamorphic rocks, if you like, pressure-cooked rocks way down in the base of the canyon. And in the walls of the canyon, the harder layers, the more resistant layers, things like the limestones, the sandstones, tend to form vertical cliffs, and the softer, more easily eroded mudstones and shales and so on, they tend to form slopes. Now, in conventional terms, these rocks span a vast amount of geological time. The Vishnu schist is said to have formed about 1.7 billion years ago by conventional dating, and that was formed by the metamorphism of yet older rocks. So we have some rocks that are thought to be extremely ancient in the base of the canyon. The youngest layer is the Kaibab limestone, which is of Permian age, and that's conventionally thought to be about 260 million years old. Now, I don't accept these dates, but those are the conventional dates that are given, just to show you the span of geological time that is thought to be represented there at the canyon. Now, about 6,000 feet of younger Mesozoic sediments were deposited on top of this Grand Canyon succession. But they've been eroded away from the area around the canyon rim, so they're not actually present there at Grand Canyon. However, if you travel north from Grand Canyon and go into southern Utah, you find that these younger sediments are exposed in a series of steps, which you can see here in this slide. It's become known as the Grand Staircase. And so you can climb up through these younger sediments. And of course, they're magnificently exposed in places like Zion Canyon and Bryce Canyon. But our focus tonight will be on the Paleozoic rocks exposed in Grand Canyon itself. Now, in this talk, I want to consider 5 important observations about the rock layers of Grand Canyon that seem to corroborate the catastrophist model of geology. If the rock layers of Grand Canyon really are the result of a global flood during which the continents were inundated with ocean water, and during which living organisms were being overwhelmed on a massive scale, we ought to be able to point to evidence that is consistent with such an account. Now, for reasons of time, as we study the 5 evidences that I've listed here, I can only give selected examples to illustrate each point, but I want to emphasize that these observations are applicable more broadly. And if you'd like further details, I just want to recommend this book, which is a book called Grand Canyon Monument to Catastrophe, edited by a geologist called Steve Austin. And that has obviously much more detail about the examples that I'll discuss and many other examples as well. So that's a book that I'd highly recommend on this topic. Okay, so here we have these 5 evidences. I'm going to think about fossils of marine organisms that are found high above sea level. Secondly, I want to think about the rapid burial of those organisms. Then I want to think about the extraordinary extent of the sedimentary rock layers exposed at the canyon. Then we're going to think about the fact that there is very little evidence of erosion between the layers, and where there is evidence of erosion, it appears to have taken place by rapid and catastrophic agents. And then I want to think finally about evidence that many of the layers were deposited in relatively rapid succession. So I want to begin, firstly, by thinking about the implications of finding marine fossils high above present-day sea level. On every continent of the world, we find fossils of marine organisms, sea creatures, in rock layers that today are well above sea level. This is certainly true when we come to study the Grand Canyon. The topmost layer in Grand Canyon is the rock formation that you can see here, the Kaibab limestone. This is a photo I took along the Bright Angel Trail as I hiked out of the canyon from the river. Now, the Kaibab limestone is the topmost layer in the canyon. It's exposed on both the south and the north rims. It's at an elevation of about 7,000 to 8,000 feet above sea level. But it's very obvious from the marine fossils found in the Kaibab limestone that it was laid down beneath ocean waters. Ocean waters that must have been laden with lime sediment, and ocean waters that must have extended across much of Arizona and beyond. Another example is the Redwall limestone, which is seen here exposed along the river in Marble Canyon. Now, this formation, like the Kaibab limestone, also contains abundant and diverse remains of marine organisms. And like the Kaibab limestone, it is an extremely widespread formation that extends across much of the North American continent. And I want to come back to the implications of that later. These are just some of the typical marine fossils that we find in the Redwall and Kaibab limestones. We have in these rocks brachiopods, lampshells, corals, bryozoans, crinoids, sea lilies and so on, bivalves, gastropods, trilobites, cephalopods, and fish remains. Many different kinds of marine organisms are represented. Now, how did they get to their present location? That's the question we need to ask. How did they get to be where they are today, so high above present-day sea level? Well, there's really only one viable explanation. At some time in the Earth's past, the ocean waters must have transgressed onto the high continents. The continents could not have sunk below sea level, because the continents are made up of lighter, less dense rocks than the rocks that make up the ocean floor. And they're lighter and less dense than the rocks that are underneath the continents, the dense mantle rocks. So there's no real way that you can make the continents sink below the ocean. The only viable explanation is that the ocean level must have substantially risen over what it is in the present day, so that the ocean waters can flood onto and over the elevated continents. Now, the question is, how on earth did that happen? What is the mechanism to allow that to happen? Now, I want to suggest that the Bible's account of the global flood suggests an answer. You see, according to Genesis chapter 7 and verse 11, the flood began with what the text says was the breaking up of the fountains of the great deep. And a careful study of the Hebrew text suggests that this passage is speaking about springs or fountains of water that are erupting in the ocean depths. That's what the fountains of the great deep seems to be referring to. And interestingly, the Hebrew word or the Hebrew phrase that's translated broken up is actually a good geological phrase, because it's a phrase that elsewhere in the Old Testament refers to earthquake activity, earth movements. It describes the breaking or the cleaving of rocks. And these fountains that broke open were open for at least 150 days, the Bible says. So the Bible gives us a picture of Noah's flood, very different from the account that's familiar to us perhaps in children's storybooks. The Bible gives us a picture of Noah's flood as a violent catastrophe that began in the ocean depths and involved the shattering, the breaking of the crust of the earth. Now, the catastrophic breakup of the Earth's crust would have released not only huge volumes of water, but also vast quantities of molten rock. And during the catastrophe, we think that the ocean floors were effectively being replaced along the mid-ocean ridges by fresh, hot flows of lava. This is the process that geologists refer to as seafloor spreading. But if you can imagine this process happening at vastly accelerated rates. Now, these hot lavas that are erupting along the mid-ocean ridges are effectively, because they're hot, they're less dense than the cold ocean floor that they're replacing, that is being subducted along the margins of the pre-flood continents. And because they're less dense, they're more expanded and they're relatively buoyant. And so what would have happened during this episode of rapid seafloor spreading is the ocean floor would effectively have been buoyed up. The level of the ocean floor would have been raised. And calculations and computer simulations that were carried out by Dr. John Baumgartner, a geophysicist, showed that this process could raise the level of the ocean floor by more than 3,500 feet, about a mile or so. Now, because today's mountains, which are relatively speaking geologically recent, because those mountains are not yet formed, and because it's very likely that during the pre-flood period the mountains, the hills, were nowhere near as high as today's mountains, a sea level rise of a mile or so is enough to inundate those pre-flood continents. So what would have happened during the flood is that ocean waters would have transgressed onto the continents, flooding them, and transporting ocean sediments and marine organisms with them onto those uplifted continents. But then towards the end of the flood, as that molten rock began to cool and as the ocean floors began to sink, sea level would have begun to fall, and the waters would eventually have drained off the continents and into the subsiding ocean basins. Psalm 104 and verse 8, which speaks of, at the end of the flood, of the mountains rising up and the valleys sinking down, may refer to that process. So here we have a mechanism that can explain the transport and the burial of marine organisms on the elevated continents, with the fossil organisms buried in sedimentary layers. And then obviously as the waters drained away, that marine life buried in those sediments was left high and dry on the continents. So that's the first observation. We have to explain how we can have widespread layers with marine fossils blanketing what are now, today, high elevated continental areas. The second observation is what I want to turn to now, and that is the evidence that these fossil marine organisms were rapidly buried under catastrophic circumstances. Now again, I could look at lots of examples here, but to illustrate this point, I want to focus upon one recent example from the Red Wall limestone. Now the Red Wall limestone, which you see here in Marble Canyon, is the most prominent cliff-forming unit in Grand Canyon. It forms this spectacular 500-foot cliff, and when you're there in a small raft at the bottom of this cliff towering above you, it really is a very spectacular sight. And the red wall here is about 500 feet thick, but actually it gets thicker. If you trace the red wall into Nevada, northwest, it gets up to about 800 feet in thickness, and then it thins eastwards into New Mexico. It's actually a light grey colour, but it's usually stained red by a coating of red clays which have been washed down from the overlying rocks. And so this high cliff stained red is obviously where the Red Wall limestone gets its name. Now in Marble Canyon we can observe all four of the divisions or members that make up the Red Wall limestone. You can see them here in this slide, including the lovely Thunder Springs member with these fantastic sort of dolomite and chert alternations that you can see exposed here. But I want to focus, for the purposes of this talk, on a discovery that was made in the lowermost member of the Red Wall limestone, what's called the Whitmore Wash member. Because in 1966, a very remarkable discovery was made in the Whitmore Wash member of the Red Wall limestone. The discovery took place here, in a small side canyon just about 100 yards or so off the Colorado River. It was discovered that exposed here in a limestone layer within the Whitmore Wash member, there was a bed of numerous large cigar-shaped fossils. Now, these fossils are the shells of large marine mollusks called nautiloids. They're a kind of cephalopod. And so from this time on, because of these nautiloid fossils, this small, otherwise pretty obscure side canyon became enshrined on the Colorado River maps as Nautiloid Canyon. Here we see one of the fossil nautiloids that you can see there. Now, in fact, it turns out that these nautiloids in the Redwall limestone are among the largest and the best examples found anywhere in the United States. You can see here with my camera lens cap for scale, you can see this shell here with the chambers of the shell exposed. Now, some of these nautiloids approach 2 feet in length, so they're quite large fossils, and they represent the remains of, as I've said, of a kind of cephalopod. That's the group that includes the living octopuses and squids and cuttlefish. Now, the only surviving nautiloid today is the modern nautilus, from which the group gets its name, a free-swimming, coiled, deep-sea mollusk that's found today in the Indian Ocean. But as you can see here, these Redwall limestone nautiloids are orthocones. In other words, they're straight-shelled nautiloids. However, like their modern counterpart, these fossil nautiloids had what was probably a squid-like animal living at one end of this chambered shell. And the other chambers were pressurized to compensate for buoyancy in a fashion that would have been similar to a submarine. So the animal was able to control its movement in the water, its buoyancy. And this would have allowed the animal to swim around. It could swim freely. It was very active, could probably move at considerable speeds through the ocean. So they must have been one of the important predators in this ancient ocean. Now, travellers along the Colorado River have often stopped to see these unusual nautiloid fossils. Again, you see one here in the rock. It's been wetted just to try and make it a bit more evident for you. However, despite this discovery in Nautiloid Canyon, the received wisdom has always been that nautiloids are very rare in the Redwall limestone as a whole. And you can see a quotation here that was from one website on the paleontology of Arizona, which said that these nautiloids are one of the rarest fossils to be found in the Redwall limestone. Well, is that correct? In actual fact, thanks to the work of a creationist geologist, we now know that that is not correct. That in fact, the nautiloids in the Redwall limestone are much more abundant than anyone previously thought. For many years, Dr. Steve Austin, who you see here, who is a creationist, he's a sedimentologist by training, he has led geological trips into Grand Canyon. He's tutored many students there. And in the 1990s, he began to take an interest in the nautiloids there in Nautiloid Canyon. And in 1995, along with a colleague, Dr. Kurt Wise, who's an invertebrate paleontologist, together these two geologists documented 71 fossil nautiloids in Nautiloid Canyon alone. And they began to consider the possibility that these nautiloid fossils represented a mass kill event, a mass kill horizon within the Redwall limestone. Now, a few years later, in March 1999, Steve was camping at Nautiloid Canyon. I think he was there with some students. And he was wondering whether these nautiloids, which he documented quite well there in this little side canyon, he was wondering whether they were perhaps more extensive still. And it so happened that instead of being on one of these large rafts, which are actually quite hard to pull up at certain spots along the river, he had with him a small motorized boat that made those otherwise inaccessible places much more accessible. So he got in his motorized boat and he went down the river and he began to stop at ledges along the river that exposed this particular layer within the Redwall limestone. And within a few days, he had discovered hundreds of fossil nautiloids that every geologist up to that point had somehow missed. They just hadn't realized that this layer was so extensive. In fact, it soon became apparent as he traced these fossils along the river that the nautiloid-bearing layer ran the entire length of Grand Canyon, the whole 277 miles. It was a massive layer packed full of these nautiloid fossils. Now, since then, Steve Austin has done a great deal of work in order to record and to document his findings. This map is one that he has published in a paper, which depicts the locations and orientations of 21 nautiloids in one location. They're on a 9 square metre horizon on a stream channel at a place called Jeff Canyon. And Steve says that the abundance and the orientation of the nautiloids at this locality is pretty typical. On average, there's about 1 nautiloid per square metre. So he estimates that in the layer as a whole, there are easily 1 billion fossil nautiloids. He thinks there could be up to 10 billion in this fossil layer. So far from being a very rare fossil, they're actually very, very abundant in this layer within the Redwall limestone. Now, what's more, there are some other strange facts about this deposit. Here we have a histogram showing the diameters of shells, of the measured shells. So here we have maximum shell diameter in centimetres and the frequency here. This is data based on 403 of the nautiloids from 3 localities, Marble Canyon, Jeff Canyon and Garden Wash. Now, the thing I want you to notice here is that we have a complete range of sizes, varying from very small, medium size, right through to large. Now, what does that mean? Well, it means that these fossil nautiloids represent an entire population that was buried at a single moment in time. This is not a natural accumulation of individuals over a long period of time. This is an entire cross-section of a population that has just been buried in one single event. Now, what's more, we know that long cigar-shaped objects like these nautiloid shells often tend to line themselves up according to prevailing currents. And Steve Austin did a lot of work measuring the orientation of the nautiloid shells in the Whitmore nautiloid bed. And he plotted the results on Rowe's diagram, showing the compass direction alignment of the shells. And what you see here in this slide are Rowe's diagrams plotted from 185 nautiloids in Marble Canyon, that's the Rowe's diagram at the top, and 152 nautiloids in Garden Wash, that's the Rowe's diagram at the bottom. Now, what they reveal, and Steve discusses this at some length in his paper, they reveal a quadrupolar orientation pattern. In other words, there are 4 dominant directions of orientation, but you'll notice that there's a deficiency of nautiloids that have their apex end, the apical end, pointing in the direction of the flow. This is a pattern that tells you that there was a strong flow in that particular direction. And so you can see here, this is the way that the nautiloids are generally oriented, and this indicates that the flow direction was in this kind of direction here, pointing towards the southwest. And here you can see the direction is roughly sort of northeast. Okay, so what does this tell us? Well, it tells us that this fossil layer with these nautiloid shells was not formed by the random fall of dead nautiloids onto a calm and static and motionless ocean floor. You know the view that most people have of how fossil deposits accumulate, animals living naturally in an environment, dying, sink into the seabed, gradually being covered by sediments. This is not how this deposit was formed. These are nautiloids that represent an entire population. They were deposited under the influence of a very strong directional current, probably in deep water. These are not animals that are simply dying and sinking in random orientations onto the ocean bed. One other very curious fact about these nautiloid fossils is their distribution within the bed. The Whitmore nautiloid bed is about 2 meters thick, and the nautiloid fossils are concentrated in the middle of that layer. Not at the top, not at the bottom, they're kind of floating in the middle of this 2 meter thick limestone bed. And furthermore, about 15% of them are standing in approximately vertical orientations within the bed. And what you can see here in this slide is actually the cross-section of one of these shells that is standing in a more upright orientation within the limestone layer. Now, what does that mean? Well, this again was another important clue to understanding how this limestone layer came to be laid down. Experiments have shown that high-speed sediment flows can develop a layered structure with laminar flow, layered flow if you like, at the base of the flow, and then a more turbulent flow at the top. This is a type of flow that geologists call a hyperconcentrated flow. And Steve Austin has proposed this as a model for understanding the flow that deposited the Whitmore nautiloid bed. And as this flow would have moved very fast, it would have been a fast-moving, pretty dense sediment slurry, if you like, it encountered a population of nautiloids living there in the water. And it picked them up. They got caught up and entrained in this flow. And what happens to objects in this kind of structured flow is that they tend to kind of float at the boundary between the laminar and the turbulent flow. So this is why the nautiloids are kind of concentrated in the middle of the bed. When this slurry came to a stop, came to a standstill and kind of froze in place, the nautiloids that had been caught up in this flow were literally frozen in place as they were carried along in the middle of the bed, many of them standing in upright positions. So let's just try and summarize this. We have here 1 to 10 billion nautiloids buried in a layer of limestone. There's a complete range of sizes showing that this is an entire population. Now, together, those two pieces of evidence tell you that you're dealing with a mass kill event, the death and burial of an entire population at one moment. Furthermore, these shells are oriented, which indicates that they were deposited under the influence of a very strong directional current. The shells are concentrated in the middle of the bed, suggesting that it was this kind of hyperconcentrated sediment flow that was responsible. In other words, this limestone bed, and remember it is of canyon length extent, it runs almost 300 miles from end to end through Grand Canyon and beyond, because you can trace this bed into Nevada. This limestone bed was not laid down by the slow and gradual accumulation of lime mud in a calm and placid ocean, which is how we normally envisage the laying down of limestone. This was catastrophic. It was a massive sediment flow that was hydroplaning across hundreds of miles of northern Arizona. And it's also worth noting, I think, that apart from the presence of nautiloids, apart from the fact that this flow happened to entrain this population of nautiloids, the characteristics of this bed are very similar to the other beds that make up the red wall limestone. So it is, in other respects, apart from the nautiloids, a pretty typical bed making up the red wall. So there we have clear evidence in that case of rapid burial, transport and burial of these marine organisms. Well, now we come to our third observation, the extraordinary extent of these sedimentary layers that we see exposed in Grand Canyon. As I noted at the beginning of the talk, the ancient sedimentary layers are usually interpreted in accordance with the principle of uniformity. The present is the key to the past. And that means that modern environments, oceans, rivers and lakes and so on, are used as models to try to understand how the sedimentary layers of the past were deposited. However, here in Grand Canyon, we encounter a serious problem for uniformitarianism, because virtually all the rock layers in Grand Canyon are extraordinarily widespread. And we know from provenance studies that many of these sediments appear to have been transported extremely long distances before they were deposited. The scale of many of these formations is much larger than the scale on which sediments are being deposited today. And it causes us to question, I think, whether this principle of uniformitarianism is really the best principle for understanding how these rocks were formed. Consider, for example, the Tapeats sandstone. Now, the Tapeats sandstone is exposed in some magnificent outcrops in Grand Canyon and elsewhere through central Arizona. You can see it here, a typical outcrop in Carbon Canyon, which is one of those canyons within the Grand Canyon, just off the Colorado River. Now, the Tapeats sandstone forms that basal Cambrian deposit. It's the basal Cambrian deposit of what's called the Tonto Platform in Grand Canyon. It's the lowermost layer that sits on top of that eroded Precambrian basement complex. And the scale of the Tapeats sandstone is absolutely extraordinary. It basically forms an enormous sheet which covers much of the North American continent from west to east and even up into Canada. But even more remarkable, I think, is the fact that similar quartz-rich sandstones characterize the base of the Cambrian, not just in North America, but on a worldwide scale. As the former president of the Geologists Association, the late Derek Ager, pointed out in his book, The Nature of the Stratigraphical Record in 1973. He points out in that book that besides these examples in the United States and in Canada, similar basal Cambrian sandstones can be seen in Great Britain, East Greenland, and even as far away as South Australia. There is a global pattern to some of the lithologies, the rock types that we see in the geological succession. Another example of this is the Redwall limestone, which we've already discussed at some length. And this is another formation that is amazingly extensive. Similar lower Carboniferous limestones stretch right across North America. They can be mapped from the Appalachians into the Midwest. But the most extraordinary thing is that if you go and look at the Redwall limestone, if you look at these other lower Carboniferous limestones in the States, and if you're familiar with the lower Carboniferous limestone that makes up the English Pennines, or that makes up the Mendips, you're not really very surprised. They're very similar. They have the same kind of sediments. It's very similar in appearance. Same kinds of fossils. Really, it's basically the same limestone. In fact, in the Avon Gorge near Bristol, the lower Carboniferous limestone is a very steep cliff-forming unit, which is even stained red by the overlying Perma-Triassic red beds, just as you see here in Grand Canyon. In fact, when I went down the river and we were looking at the Redwall limestone, I said to the geologist I was with, "Why did you bring me all this way, right across to Arizona to see a limestone that I can see back at home? This is basically the same stuff." Now, these lower Carboniferous limestones have even been traced into Asia. There's a very thick limestone exposed in Kashmir, which Derek Ager once again says is very similar to its British equivalent. It has exactly the same kind of fossils in it. It looks just the same. Now, this is so unlike what we see in the present day. Derek Ager, in his book, later book, The New Catastrophism, published in 1993, said this on page 100. "At the present day, we are sadly lacking in carbonate, that is, limestone, deposition, especially in shallow water environments. Apart from very local examples, such as the overworked Bahamas banks in the Caribbean and Sharks Bay in Western Australia, there is also some forming the coral rock down the east coast of Africa and on the west side of the Persian Gulf, but these are nothing compared with the vast extent of shallow water carbonates at particular moments in the geological past. Is the present really the key to understanding the past? Or is there something going on in the past that is very different to what we see happening in the present? That's what I think the evidence is telling us. Let me give you just one final example of this phenomenon before we move on to the next evidence. The Coconino sandstone. Now, the ribbon of cream-coloured rock, which you can see there just below the rim of Grand Canyon, is the Coconino sandstone. It occurs on both the north and south sides of the canyon. It stretches from east to west as far as you can see. It's a very prominent layer that stands out to the observer. And at the moment, I'm particularly interested in the Coconino sandstone because, along with two colleagues, I'm engaged in a 5-year project studying the depositional history and the depositional environment of the Coconino sandstone. I don't want to say too much about that this evening, but I just want to to draw your attention to how enormously widespread this layer really is. The Coconino sandstone and its equivalents constitute an enormous layer of sand that covers large parts of Arizona, New Mexico, Texas, Oklahoma, Kansas, and Colorado. The area covered by this sandstone formation is about 200,000 square miles. And the contour lines that you can see on this map indicate the thickness of this layer in feet. It averages about 315 feet thick. It's actually a kind of a wedge shape, so it gets thicker towards the south and thins out towards the north. But on average, it's about 315 feet thick. And it's estimated that the volume of sand in this one formation is about 10,000 cubic miles. So it is an absolutely vast layer of sand. Now, where did the sand in the Coconino sandstone come from? Well, we can study the minerals, and the quartz grains which dominate and the minor portion of feldspar grains are thought to have come from the erosion of crystalline rocks like granites or gneisses or schists, or possibly by the reworking of earlier sand deposits. Now, when we study the cross-bedding, which is a kind of dune structure that's found in this sandstone layer, when we study the cross-bedding, we can tell the direction from which the sand came. And it appears to have been transported predominantly from the north. So we want to look, if we want to find the source of the sand grains, you want to go to the north. The problem is that there is no source of sand grains to the north, at least anywhere that's close by. Along its northern occurrence, the Coconino rests on the Hermit Formation. Now, the Hermit Formation has a finer grained texture than the Coconino sandstone. So the Hermit Formation can't be the source of the sand. Can't be the erosion of the Hermit that gave the sand, because it's too fine. So where do we get the sand from? Well, we're really forced to conclude that the sand in the Coconino sandstone was transported a very great distance. And it's still not really certain where that sand came from. It may have come from a long, long way to the north. Some people have speculated the ultimate source may be the Appalachian Mountains, but certainly it's been transported a very long way. That is utterly unlike the kind of patterns of erosion and transport and sedimentation that we see going on today. It just seems to be on such an enormous scale compared with the present. And this brings me to a related point. On the present-day Earth, sediments are being carried towards and within the ocean in all directions, okay, because of local topography and so on, river drainage systems. Material is being transported in lots of different directions. So if the present is the key to the past, when we look in the geological record and we find things that indicate the direction of ancient currents, things like fossil ripple marks, fossil dune structures, what they should show to us is a random pattern, because that's what we see basically on the continents today. We see, and within the ocean, we see random patterns basically determined by local scale and regional scale topography, movements, and so on. So we would expect something that's random. However, a geologist by the name of Arthur Chadwick, over many years, has been collecting what's called paleocurrent data. This is data from rocks, looking at structures that give clues as to directions of currents. He's amassed 500,000 paleocurrent direction measurements. I mean, that's a massive sample of data by anyone's standards. And he's still not happy. He still goes on collecting more and more. But he's got 500,000 measurements or so, and he has a website. There's the web address if you want to go and look at his maps. He's got maps of different continents of the world for different geological periods and so on, and he gives you the paleocurrent data. Now, what's really interesting is what his data has revealed. He's written some papers on this. You can find those on the internet, and some of them published in the geological literature. What you see on the left here is a map of the North American continent showing the prevailing current directions during the Paleozoic. And on the right, the same continent, North America, with the prevailing current directions during the Mesozoic. Now, throughout the Paleozoic, in other words, the time that's represented by those horizontally bedded Grand Canyon sedimentary rock layers, there is a stable and a pretty consistent pattern of currents flowing roughly northeast to southwest across the entire continent. Then, in the Mesozoic, the current directions seem to shift. Now, these are the sediments that are represented by those younger sediments sitting on top of the Grand Canyon sequence that are exposed in the Grand Staircase. And the direction shifts, but again, it's then consistent throughout the Mesozoic in a broadly easterly direction. What's interesting is that as you approach the present day, as you get up into the Cenozoic rocks, the consistent pattern is lost. And there's no discernible continent-wide pattern once you get up above the Mesozoic into the Cenozoic. And he found a similar pattern on the other continents of the world. Now, this is really interesting. What is the explanation for what he calls these megatrends in paleocurrents? The creationist has an explanation. Because the Paleozoic and the Mesozoic, in the creationist view, represent a time when the North American continent was being flooded by the transgressing ocean during a global scale event. They don't represent hundreds of millions of years of processes similar to those going on today. They represent global scale processes on a much shorter time scale. And so, consistent continent-wide patterns might be expected. Consistent currents across the entire continent. The Cenozoic rocks, the more recent rocks, which display no overall continent-wide trend, are usually understood to be either late flood or post-flood in age, when a more normal pattern of drainage was being re-established following that global event. So the creationist has an explanation for these patterns. But what is the uniformitarian to make of these patterns? If the present is the key to the past, these consistent continent-wide megatrends are utterly unlike anything that we observe today. And yet they must have persisted for hundreds of millions of years of geological time. So I think here we have more data that favours the global flood theory rather than the uniformitarian explanation. Okay, our fourth observation. This concerns the apparent absence of substantial time gaps in the Grand Canyon succession. The evidence that the sedimentary layers themselves were laid down rapidly seems, on the face of it, to be very persuasive. However, there are undoubtedly gaps in the record when no sediments were being laid down, or when erosion removed sediments that had previously been laid down. And this block diagram of Grand Canyon that you see here shows the position of the most important gaps that are claimed in the Grand Canyon sequence. Now, some are undoubtedly real. There really are some time gaps. Others are more doubtful. The question is it possible that large amounts of time could have passed during these time gaps? Now, we don't have time to look at all of these examples, so I've selected three of the more significant ones. Firstly, I want to look at the contact between the Coconino Sandstone and the Hermit Formation, just here. Then I want to look at the contact between the Red Wall limestone and the underlying Muave limestone, and it's got a bit of what's called the Temple Butte sandwiched in between. And then I want to look at the Great Unconformity, the most significant time gap, if you like, in Grand Canyon, which is between the horizontal Tapete sandstone and the underlying tilted and eroded Precambrian basement. Now, in the first two cases, the Coconino Hermit and the Temple Butte unconformity, there is very little or no evidence of erosion as we'd expect if the sedimentary layers really were exposed as either an ocean surface or a land surface for prolonged periods. Obviously, in the third case, the Great Unconformity, there is evidence of substantial erosion, but I want to argue that rapid and catastrophic agents were responsible for this erosion. So let's begin with the first example. Thousands of visitors have a very vivid impression of this abrupt boundary between the cream-coloured Coconino Sandstone and this reddish Hermit Formation underneath as they walk along the Bright Angel Trail in Grand Canyon. And interest in this contact between these two rock formations has been increased in recent years by the discovery of a thick formation that is sandwiched between the Coconino and the Hermit Formation in central and eastern Arizona. It's a formation called the Schnebly Hill Formation, and it approaches a thickness of 2,000 feet beneath Holbrook in Arizona. Now, the fact that you've got this very thick formation elsewhere in Arizona between these two formations has led geologists to suggest that more than 10 million years passed at Grand Canyon between the deposition of the Hermit and the deposition of the Coconino. However, take a look at that contact. I wish I could take you there and you could have a close look at this contact. Because when you examine that contact very carefully, you can find no significant physical evidence of erosion at all. Just isn't any. It is an extraordinarily flat surface, free of any kind of channel erosion as you'd expect if that surface represented a long time period. There are no pebbles of Hermit Formation embedded in the base of the Coconino. There's no soil or weathering profile in the top of the Hermit. So it seems, on the face of it at least, very difficult to make a case for 10 million years of geological time. If there is missing time there, and it seems that there is some missing time, it must be much shorter than 10 million years. When we come to our second example, which is the Temple Butte unconformity between the Red Wall limestone and the underlying Muave limestone, we actually do find, in this case, some physical evidence of erosion. As you can probably see here, channels have been carved into the Muave limestone. Here's one of these channels. And it's been infilled by this limestone formation called the Temple Butte limestone. So we do have some evidence here of erosion. Here's another example of one of these channels. So there is a time gap. The question is, how much time? From a conventional point of view, two entire geological systems are missing here, the Ordovician and the Silurian. So if conventional dating is right, that means that those channels represent a time gap of about 100 million years or thereabouts. Massive amount of missing time. But the only evidence of 100 million years of missing time is about 30 feet of channeling, a slight surface relief. Now, is such a long time gap really justified by the physical observational evidence? The carving of channels, especially if the underlying sediments were poorly cemented, but even if they were well cemented, the carving of channels 30 feet deep does not require long time intervals. Certainly doesn't require 100 million years. But that is effectively the only evidence of that vast time period between the Red Wall and the Muave. Now, the most noteworthy unconformity in Grand Canyon, of course, is the Great Unconformity, which occurs between the Precambrian basement rocks and the overlying Tapete sandstone. And here you can see the Great Unconformity from Lipan Point on the south rim. This is the unconformity surface that you can trace along here. You can see here the tilted Precambrian layers. We have the Docks Formation, the Cardenas basalt, and then on top we have the Tapete sandstone. Now, the conventional view is that the erosion of these Precambrian rocks took place over many millions of years by very slow and gradual processes. Dr. Davis Young, a geologist in the USA, expresses here the conventional view of the Great Unconformity. He says this: the observed features indicate that the unconformity is an ancient land surface that experienced gentle weathering and erosion over a long period of time before being submerged beneath a gradually encroaching sea. Now, will you note the language that he uses there in that description? This was a land surface. It was subjected to gentle weathering over a prolonged period of time before it was submerged gradually beneath an encroaching sea. Uniformitarianism is involved, obviously, there in that description. Now, everybody agrees that there has been significant erosion on this boundary. Of course there has. But how did it happen? Creationists suspect that the erosion of that Precambrian basement occurred rapidly by catastrophic agents. So, to help us decide whether this view is correct or the catastrophist view is correct, what clues ought we to look for? Well, here we have the Great Unconformity close up. At this particular locality, the rocks below the unconformity are part of the Precambrian Nankoweap formation, and it's the Tapete sandstone that you see above the unconformity. And Steve Austin there has his thumb and his little finger on the two sides of the unconformity. The time gap represented between his thumb and his little finger is thought to be about 500 million years, represented by that erosion surface. Now, if the rocks at that erosion surface had really been exposed at the surface, either in the ocean or indeed as a land surface, as Davis Young claims, for such an enormous period of time, we'd expect to see evidence of that. There should be evidence at this surface. There should be evidence of very deep and extensive chemical weathering of the underlying rocks. We should see evidence of oxidation, acid leaching, the alteration of the minerals. We might expect to find some kind of weathered residue, a soil, something of that kind. However, when we study this surface close up, what we find is that the evidence of chemical weathering, soil profiles and so on is basically missing. It's not there. In fact, in some places there are minerals in the rocks directly below the erosion surface that would definitely have been unstable had they been subjected to chemical weathering during periods of long exposure. And yet they're there in a fairly pristine state. Now that suggests that this surface was broken up mechanically, that there was physical erosion of this surface, but it appears largely not to have taken place with accompanying chemical effects. There was not chemical weathering on this surface. It was effectively physical, mechanical erosion. So what could have been responsible for physically eroding this surface? Well, certainly we need catastrophic kinds of processes. And recent studies by geologists have in fact suggested that the Tapete sandstone, at least near its base, at the basal section of this sandstone layer, was actually deposited by catastrophic debris flows that simultaneously broke up and transported enormous blocks of the underlying Precambrian rocks in a matrix of sandstone. And these flows were deposited on an eroded surface that has more than 140 metres of vertical relief, which actually indicates that the water depths must have been about 200 metres or more. That's considerably deeper than most people had previously envisaged. Most people were interpreting the Tapetes as a shallow water deposit. It looks as if it was in deep water, and that there are these catastrophic debris flows. And here you see the base of the Tapete sandstone east of Clement Powell Butte, just above the Great Unconformity, and the large boulder that I've highlighted there is a boulder that's 15 feet in diameter. It's estimated to weigh nearly 200 tons, and it's a block of Shinamou quartzite. It's been moved at least a quarter of a mile from the nearest exposure of Shinamou quartzite. So this was a flow that was capable of transporting enormous blocks of rock. And such a flow would certainly have been capable of deeply eroding the bedrock over which it was moving. This is not evidence of gentle weathering and erosion on a land surface. This is evidence of rapid and catastrophic activity on a deeply submerged surface, which is consistent with the global flood model. Okay, well now I'm looking at the clock and realising time is racing away. Now we come to the final observation I want to consider in this talk, which is the evidence that points to many layers, many strata having been formed in rapid succession and not separated by hundreds of millions of years. This slide shows some pretty dramatic folding of the Tapete sandstone in Carbon Canyon within the Grand Canyon. And no doubt you can see the people here. That gives you some sense of the scale. Here we have the Tapetes. It's roughly in a kind of horizontal orientation here. And then it goes into this sort of dramatic upwarp here where the rocks are now in a vertical orientation. Now, rocks that are lithified, in other words, sediments that have been turned to solid rock that have been well cemented, they tend to behave in a hard, brittle fashion when they're deformed. They don't tend to act in a soft and plastic fashion. And normally we can determine the style of folding, the style of deformation in any particular case by a close examination of the rocks involved, particularly using microscope studies to look at the grains under magnification. And in this case, the evidence strongly supports the idea that the Tapete sandstone was still soft and unconsolidated, uncemented at the time it was folded and deformed. because instead of fracturing like the underlying crystalline basement rocks did, the Tapete sandstone instead kind of draped itself over the structure that caused the folding. It didn't fracture. It just draped itself. It thinned out and stretched, if you like, over that structure. And when you look under the microscope at the sand grains, they show no evidence that this material was cemented, because none of the grains have been broken or elongated. The mineral cements have not been broken and then recrystallized. So the evidence suggests pretty strongly that this sandstone was still soft and pliable when it was deformed. Now the next question is then, when did the folding occur? Well, we know that the folding was related to the formation of a structure called the East Kaibab monocline. In other words, the uplift of the plateau through which Grand Canyon is actually carved. The Grand Canyon sequence extends over 400 kilometers into eastern Arizona, and when you go into eastern Arizona, you find the same rock layers, but they're at least 1 mile lower in elevation. And that's because the uplift of the Grand Canyon region has caused this enormous fold in the rocks, the East Kaibab monocline. Now we know that that folding event must have happened after the deposition of the Kaibab limestone, because the Kaibab limestone is also folded by the same event. In fact, it's thought that this folding occurred in the late Cretaceous, about 70 million years in the conventional timescale, and then continued through the Cenozoic. So it's thought to be relatively recent deformation. Now let's just think about the implications of that. The Tapete sandstone is a Cambrian sandstone, deposited somewhere around 540 million years ago, something like that. The Kaibab limestone is about 250 or more years younger in conventional terms. The folding is probably something like 450 to 500 million years after the deposition of the Tapete sandstone. And yet the Tapete sandstone was still unconsolidated, soft and pliable when the folding took place. Is it possible for the Tapete sandstone to have remained unconsolidated for that length of time, particularly when it was deeply buried? Because the factors that should have promoted the lithification of the Tapetes were present: deep burial, elevated temperatures, high pressures driving out the pore waters. It should have been cemented, and it wasn't after all that time. Now, it just seems more consistent with a view that says, actually, there's not that much time separating the deposition of the Tapetes and the uplift that then folded it. That seems to make more sense. Now, we see another somewhat similar example. I'll cover this very quickly because of time. We find that in many localities, when you go to look at that horizon, which we've already looked at, the boundary between the Coconino Sandstone here and the Hermit Formation, there are many localities where along the boundary between the two, we find that there are cracks in the top of the Hermit Formation into which sand from the Coconino Sandstone has fallen. So we've got these sand-filled cracks. Now, conventional geology has usually interpreted these as having formed in a desert environment. The idea is this: the Hermit Formation is uplifted from the ocean, it's high on the continent, it's maybe a dry, mud-cracked plain, desert plain, and sand gets transported across this dry, mud-cracked plain, and the sand drops into the cracks, into the mud cracks, and forms these sand-filled cracks. However, my colleague John Whitmore, who has studied intensively these cracks in many, many localities around Grand Canyon, both on the south and the north rims, has found many features of these cracks which strongly suggest that they are not formed by desiccation mud cracks. He finds, for example, that they are not regularly spaced like desiccation cracks. He finds that they often widen downwards rather than just upwards, as desiccation cracks do. He finds that sometimes these sand-filled cracks are even attached to lateral sand bodies within the hermit formation, unlike what you'd expect with desiccation cracks. So he doesn't think they're desiccation cracks at all. He thinks instead the evidence strongly points to a tectonic origin, an earthquake origin. He thinks that they are the result of Coconino sand falling into cracks that opened up in the hermit formation when earthquakes shook the hermit. Okay, so the hermit gets fractured by the earthquake and then sand falls into the crack. And one of the most compelling lines of evidence that he's found for this is that when you look at the size of the cracks, the width and the depth and the depth is greatest along the Bright Angel Trail in Grand Canyon. If you go to the east, if you go to the west, if you go to the north, the cracks get smaller, they get shorter, and they get narrower. And in fact, they disappear completely as you go well to the east and the west. Now, why is that interesting? Why should they be biggest along the Bright Angel Trail? Well, the Bright Angel Trail runs along a major fault line. The biggest fault that runs through Grand Canyon, the Bright Angel Fault. So he suggests that actually the Bright Angel Fault is responsible for these sand-filled cracks. It was the movement along that fault that caused the fractures to open up in the hermit formation, and then the sand fell into the cracks. However, there are some interesting implications for geological timescales if that's the case. Because it is known that the Bright Angel Fault was only active during two parts of geological history. There was initial movement back in the Precambrian, and then it was reactivated up in the mid to late Cenozoic, way up here. And those are the only two movements along the Bright Angel Fault. Now, the Coconino sandstone was deposited here in the Permian. Okay, so we have the Coconino sandstone here. Now, if the cracks that opened up in the hermit were the result of this reactivation of the Bright Angel Fault, that means that the Coconino sandstone must still have been unconsolidated and full of fluid in the late Cenozoic in order to fall and be squeezed into those tectonic cracks. Now, it just seems more plausible to us that instead of there being a timescale of about 200 million years separating the deposition of the Coconino and the point at which that wet sand was then injected into cracks in the hermit, it makes much more sense if we kind of tie these layers together and we compress this timescale into a much shorter period. So let me conclude then by just briefly summarising the 5 things that we've looked at this evening. Firstly, we've got the abundant remains of sea creatures preserved in the sedimentary rocks of Grand Canyon, thousands of feet above present-day sea level, and they are a testimony to the inundation of the North American continent by transgressing ocean waters in the Earth's past. Then secondly, we have the extensive fossil graveyards and the exquisite preservation of many fossil organisms, including that mass kill horizon in the red wall limestone, which points to the large-scale destruction of life and the rapid formation of those sedimentary layers. Thirdly, we have the fact that individual sedimentary formations and those that correlate with them can be traced across entire continents, even between continents. Rock layers like the tapetes, the red wall, the Coconino, which seems to indicate depositional processes on a scale much larger than those of the present day. Fourthly, we have those flat knife-edge boundaries like the one between the Coconino and the Hermit Formation, which indicates that there wasn't much time separating them, that there was almost continuous deposition. And where we do have erosion that's evident, it appears to have taken place by catastrophic agents. And then fifthly and finally, we have the layers folded without fracturing or injected into cracks while still in an unconsolidated state, which suggests that the episode of deposition was not separated from the episode of folding or deformation by a long period of time. So in conclusion, far from being a showcase for uniformitarian geology in millions of years, flood geology is alive and well and kicking in Grand Canyon. Thank you. These two competing interpretations of the geological record in diagrammatic form. In the middle of the screen you see the standard geological column, a somewhat simplified version of it, with the Precambrian rocks, the Paleozoic rocks or primary rocks, the Mesozoic or secondary rocks, and then the Cenozoic rocks. And on the right, you can see the evolutionary or long age interpretation of this geological succession. Now, the evolutionary or long age view sees the rocks and fossils as a record of evolution over geological timescales. And this perspective is founded on the principle of uniformitarianism, the idea that the present is the key to understanding the past. In other words, we observe today the laying down of sediments in modern-day rivers, lakes, oceans and deserts, and we assume that the ancient fossil-bearing sediments, like those that we see exposed at Grand Canyon, were formed by similar processes and at similar rates and intensities to those that operated in the past. What is normal or average today is assumed also to have been normal or average in the past. Now, of course, if that uniformitarian principle is correct, then the rock layers of Grand Canyon must have taken tens or even hundreds of millions of years to have been laid down, because sediments today are accumulating in these modern environments on average very slowly. So for many people then, Grand Canyon, with a mile-thick succession of sedimentary layers, is a showcase for slow and gradual geological processes acting over long time spans. However, on the left of this diagram, we see the alternative view, or one alternative view, the creation or the young age interpretation of the geological record. While the uniformitarian geologist adopts the idea that the present is the key to the past, the biblical creationist sees the rocks and fossils instead as snapshots of depositional events at specific times. Grand Canyon attains a depth of more than a mile, and it ranges from 4 to 18 miles wide. And Grand Canyon, along with its 60-mile connection here through Marble Canyon, isolates virtually the entire northwestern corner of the state of Arizona. This is a photograph that I took at sunset on the south rim of Grand Canyon at a place called Mather Point. The south rim of Grand Canyon is at 7,000 feet above sea level. The north rim is just a little higher at 8,000 feet in elevation. And the Colorado River cascades along within the canyon at about 2,500 feet above sea level. And within the canyon, as you can see here, there's a host of pinnacles and buttes, canyons within canyons, precipitous gorges and ravines. The most spectacular of these pinnacles or spires are sometimes referred to as temples, and some of them tower up to a mile or so above the level of the river. Now, of course, this is a desert landscape, and what that means is that we don't have very much vegetation. And of course that's great for geologists, because it means that the rock layers are exposed magnificently to view, and also for the photographer it allows the sunlight to pick out the varied colours and hues on the rock. And as you watch the sun go down over the canyon, the colours just seem to change all the time. It really is a magnificent sight. Well, let's think then about the geology of Grand Canyon. Grand Canyon exposes a thick sequence of Paleozoic sediments, beginning with the Tapete sandstone here and going up to the Kaibab limestone, which forms the rim. These horizontal sedimentary layers sit on top of an eroded basement of older Precambrian rocks, including sediments, Precambrian sediments like the Bass limestone, the Hakatai shale, the Shinamou quartzite, the Docks formation. There are also igneous rocks like the Cardenas basalts, which are lavas, and various sills and dikes that have been intruded in biblical history. Notably, he interprets a large portion of the geological record as the product of a global flood, the flood that's described in the Bible in Genesis chapters 6 to 9, with other parts of the record representing pre-flood and post-flood deposits. And although there's today still a great deal of debate among creationists about precisely where these boundaries between the pre-flood and flood and post-flood sediments lies in the geological record, the view that I've represented here is one major strand of thinking within creationism, with most of the Precambrian rocks representing Creation Week and pre-flood deposits, and the uppermost part of the Precambrian through to the end of the Mesozoic, representing flood rocks, and then with the Cenozoic rocks representing those that were formed in the post-flood period. Now, in this catastrophist framework, the present is not viewed as representative of the Earth's past. Instead, there's perceived to be a major discontinuity between the past and the present. The global flood described in the Bible is accepted as a real and unique event that was responsible for depositing many of the Earth's sedimentary rocks, including many of those that we see in Grand Canyon. So in my talk today, I want to describe just some of the geological evidence, and I have had to be selective for reasons of time, that appears to be consistent with this catastrophist interpretation of the geological record. Evidence which offers us, I think, some helpful insights as we seek to understand the geology of Grand Canyon. But before we look at the evidence in detail, I thought it would be helpful to begin, first of all, with an overview of Grand Canyon itself and its environs. So here we have a map of the Grand Canyon in its setting in the state of Arizona. Grand Canyon stretches 277 miles through northern Arizona, from Lake Powell in the east right through to Lake Mead in the west. The main portion included into these sediments. There are also igneous rocks like granites, the Zoroaster granite, and also the oldest rocks are thought to be these various schists like the Vishnu schist. They're metamorphic rocks, if you like, pressure-cooked rocks way down in the base of the canyon. And in the walls of the canyon, the harder layers, the more resistant layers, things like the limestones, the sandstones, tend to form vertical cliffs, and the softer, more easily eroded mudstones and shales and so on, they tend to form slopes. Now, in conventional terms, these rocks span a vast amount of geological time. The Vishnu schist is said to have formed about 1.7 billion years ago by conventional dating, and that was formed by the metamorphism of yet older rocks. So we have some rocks that are thought to be extremely ancient in the base of the canyon. The youngest layer is the Kaibab limestone, which is of Permian age, and that's conventionally thought to be about 260 million years old. Now, I don't accept these dates, but those are the conventional dates that are given, just to show you the span of geological time that is thought to be represented there at the canyon. Now, about 6,000 feet of younger Mesozoic sediments were deposited on top of this Grand Canyon succession. But they've been eroded away from the area around the canyon rim, so they're not actually present there at Grand Canyon. However, if you travel north from Grand Canyon and go into southern Utah, you find that these younger sediments are exposed in a series of steps, which you can see here in this slide. It's become known as the Grand Staircase. And so you can climb up through these younger sediments. And of course, they're magnificently exposed in places like Zion Canyon and Bryce Canyon. But our focus tonight will be on the Paleozoic rocks exposed in Grand Canyon itself. Now, in this talk, I want to consider 5 important observations about the rock layers of Grand Canyon that seem to corroborate the catastrophist model of geology. Well, thank you very much for that welcome, and thank you for your invitation to come up to Scotland and to speak here in this great city, and a city that obviously has many geological connotations, many geological associations over the years. So it's great to come here and be able to talk to you on this subject of geology. Now, somebody is telling me they can't hear very well. Can you hear me okay? Yeah? Is the microphone working? I'll speak up slightly. Okay. Well, the subject this evening is the Grand Canyon, evidence for the global flood. So we're not really dealing with the geology of Scotland, some local geology. We're going a bit further afield. And we're going to Arizona. The Grand Canyon in Arizona is one of the world's greatest natural wonders, of course. And about 5 million people every year visit the canyon and wonder at the magnificence of the spectacle that's spread out before them. The sheer size and the majesty of the canyon have a tendency to overwhelm the visitor and surpass your ability, really, to take in the sight that's spread out before you. Now, one of the questions that commands our attention at Grand Canyon is what on earth it all means. How did the rock layers that make up the canyon come to be there? What story about the past do these rock layers reveal? What is their origin? Now, the explanation that's presented to most visitors involves slow processes operating over very long time periods, periods of hundreds of millions of years. However, in this talk, I want to propose that there is an alternative explanation for the Grand Canyon and for its rock layers, an explanation that involves catastrophic geological processes operating over relatively short timescales. And I want to suggest that gives us an alternative explanatory framework that helps us to understand the geology that we have laid out before us. Now, here in this first slide, we see